heat pumps. And then we'll talk about connection between entropy and the second law of thermodynamics. So I kind of skipped the things after that. If you're interested about order and disorder and statistical interpretation of entropy in second law, you can read it for your general knowledge, but I don't include that in exam. Okay, so what is thermodynamics? It is a study of processes in which the energy is transferred in the form of heat and in the form as work. So the change in internal energy of a closed system will be equal to the energy added to the system minus the work that's done on its by the system on its surrounding. And here the wording is kind of important. What kind of work is done, whether it's done by the system or on the system, or is it done by the surrounding or on the surrounding? And so hence the sign, whether it's minus or plus, will be defined by this wording. So what is heat? Heat is a transfer of energy due to change in temperature. So we saw in the previous chapter that heat can be defined as the mass times some specific heat of a substance times the change in temperature, delta T. So where delta T is the difference between the final and the initial temperature of that of the system. So when you have, when you have the change in temperature, the heat transfer happens. Of course, there's also another way of having heat, which we call latent heats, if you remember, when there is a phase change of that matter. For example, solid to liquid, like ice melts, becomes water, and that happens at constant temperature. But in that process, still there is heat transfer, and it's called latent heat. But the other heat that we're going to talk about here, due to the change in temperature, so that's the heat we're going to be talking about. And work is is transfer of energy, but it's not due to the change in temperature. So when we do work, there is no change in temperature, but still energy is transferred. So the internal energy is defined as the total sum of all the energies of the molecule in that system. So if you have one molecule, it will have a certain amount of internal energy. You have more molecules, it will have more internal energy. So more molecules means more internal energy. And so internal energy increases if the work is done on the system. So let me write that part. So the internal energy we define it as delta U or E internal. So anyway you want to give it a definition, internal, or it's the same as delta U, change in internal energy, will increase like that if work is done on system. So here it's a little confusing, on system. And internal energy will decrease if the work is done by the system, on the surrounding, on the surrounding. So you can do work on the system or on the surrounding. Okay, so we'll see. Okay. And this is the change in internal energy given in this equation, that's equal to the energy that added to the system and work done by the system on the surrounding. And if it will be the work done, so this is by the system, by system. And if the work is done on the system, then the work becomes negative, and this part becomes positive. So it's going to be heat minus work done on system, then this sign will become positive here. So if it's on system, so we'll do. When reading the problem, pay attention to the wording which asks whether work is done on or by, so that you can properly account for the sign. And this is a another way of representing the conservation of energy. And it's written in terms of useful to system that involve heat transfer. So if we rewrite the conservation of energy as we did, including potential and kinetic energies here, so you'll see that the internal energy will also be added some kinetic and potential, changing kinetic and potential energy. So this will be the more complete form of the first law of thermodynamics, including those energies as well. So, include this part. So using the first law, we can look at one simple example. Let's say we have 2,500 joules of heat added to a system, and 1,800 joules of work is done on the system. And we want to know what is the change in internal energy of that system. So going back to the wording that I was talking about, whether it's on or by the system work done. So if it's work done on the system, then it's going to be negative. That means when we apply work, what's written here? So when we apply the first law of thermodynamics, we will have to include the work that's done on system to be negative. And so the amount of heat added to the system is 2,500. The work is done on the system is going to be negative 1,800. And so the change in internal energy will be positive, which means it will increase. And it's going to be equal to 4,300 joules. Okay, so again, it's important to keep track of signs by carefully reading the problem when it's asking. So the work done on the system. Okay. 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 So let's look at another example. The kinetic energy that transforms into thermal energy. So if we have a 3-gram bullet traveling at a speed of 400 meters per second and entering a tree, and it exits the other side with a speed of 200 meters per second. So good way of starting any problem is to draw a picture of things that happening, right? The diagram or sketches or anything that will be helpful visualize the problem. So here I'm going to give an example, like for example, their bullet is traveling at certain velocity and it's going to enter a tree, right? And then come out from the other side. So the initial velocity is 400 meters per second. And as it enters the tree and comes out here, So it's going to go a little slower. So I'm going to make a smaller arrow here to show, and it comes out with the velocity of v2. Or we can do it initial and final velocity. Okay, that will work too. I have it here, initial and final. And the question here will be, where did the bullet's kinetic energy go? So obviously we can see that it was going faster, and then after going through the tree, it slowed down. And how much energy was transferred in this process? So kind of give me an ideas what kind of what happened in this process. So if anyone can guess or tell me what do you think happened to the energy? Did it disappear, or there was some kind of a transformation from one type of energy to another? Well, if you read the title of the problem, it kind of tells you what's going to be happening to the kinetic energy of the bullet. It is going to be transformed to thermal energy. So in this process, what we get is transformation of one type of energy to another. So the energy of motion is transformed to a thermal energy. And so we're going to see how it happened and how much was lost in that process. So kinetic energy transformed to thermal energy. And where did that energy was lost? So because this is, we're going to consider it as use conservation of energy concept as well, we can look at some other terms that are involved in this process. So in the previous, we had for the first law of thermodynamics to include all the energies, which will be kinetic energy, potential energy, the work, and change in internal energy, right? So all these terms, we're going to see contribution of each term in applying this law to this problem. We can assume that there is no potential energy involved in this process. We're going to take this as our closed system, isolated closed system, and also consider that no work is done by the system on the surrounding. So we're only looking at these two things, and nothing else from outside is bothering. So this is traveling pretty fast, and the kinetic energy much higher than any potential energy that it could have, but actually doesn't have because it's going like in a straight line. So this term will be 0. The work also will be considered to be 0 because no heat is added to the system from the surrounding. Then it means that the kinetic energy gets transformed to the internal energy. So no heat is added also, so this one is also 0. So the all kinetic energy is transformed to internal energy. Oops. Plus delta U is equal to 0. So if we rewrite it in all terms. Or that means that the change in potential energy, kinetic energy is equal to negative change in internal energy, or the other way around. The signs doesn't matter. We can put negative here, positive here. Let's redo this way. So the change in kinetic energy is final energy minus initial minus delta U. So if we rearrange the signs, what we get here, flip this, we'll get initial minus final is equal to delta U. So for the initial kinetic energy, we have 1/2 mv initial square minus 1/2 mv final square for these values. And if we do plug them in and find the change in kinetic energy, we can see that it's equal to let's see. So the 3 grams will have to convert into kilograms. That will be 3 times 10 to the -3 kilograms. And this meters per second are good. So 1/2 times 3, here we'll have 400 square minus 200 square. So that gives us the internal energy of 180, I get it right, yeah, 180 joules of the energy. So the internal energy of both increase, right, by 180 joules. But if we use the bullet as one system, then as our system, so not the whole thing, but like let's say it's only a bullet is our system that we're considering, then the work would be done on that we'll have to consider the work here. We can't assume that it's 0, and the heat transfer would also occur, so the heat will also be involved. And so you can see that the importance of choosing the system in a convenient way that you can eliminate a lot of variables here. So since we have chosen our system to be the whole thing together, it's closed system, no heat transfer goes in and out of our system, no work is done, so these terms become 0. But if we choose our bullet to be just our system, then because it's going to be interacting with the surrounding, so the work is going to be done on the surrounding, and the heat transfer is also going to be happening between our system bullet and the surrounding, which will be a tree in this case. So it will be a little more complicated problem. Okay, so we made it simpler by eliminating some terms, by choosing correct type of system. Right. Okay. So we'll talk about thermodynamic processes and first law. So there, just before I go there, the statement of the first law of conservation of energy is another way that it's stated by the first law of thermodynamics. So it's kind of a general statement of the law of conservation of energy. And the work and heat are involved in thermodynamic processes and change the system from one state to another. And by state, what we mean is the physical properties such as pressure, volume, temperature, mass, the number of moles. These are called state variables. So change of those variables will consider a change of state from one change of system from one state to another. But the work and the heat, for example, they're not considered to be states. So they're not the states. The states are the pressure. So we'll just define this state of the system. So pressure, volume, temperature, mass, number of moles, and we also can take that. And so those are the states of a system. So you can change those states. But work and, actually the internal energy as well, not it here. But the work and heat, they are not states of the system. Okay, no states, not states. And so we'll see how we're going to apply this first law of thermodynamics processes to the change of the states of the system. So we can have, let's look at the main three states that we're going to work with now: pressure, volume, and temperature. And it's important to change, keep something constant and then change some other things. So we're going to look at isothermal process, where we assume that the temperature is going to be constant, and the change in temperature will be zero because the temperature is constant. But then the pressure and the volume are going to be changing, and the way they look, if you look at the relationship of pressure dependence on the volume, we'll have this type of curve. And if we have ideal gas, remember the equation of the ideal gas, that pressure times volume is equal to number of moles times gas constant and the temperature. Then, because the temperature is constant, change in temperature is zero. That means that the pressure times volume is going to be also constant. And the mass is going to be also kept constant. And so the change in internal energy also going to be equal to zero, because we know that the change in internal energy in terms of depends on change of temperature. Right. And so because that temperature is constant, then the change is zero. So that makes our change of internal energy also being zero. And going back to the defined first law of thermodynamics, where we had the definition of, so this is going to be also equal to zero. That means the amount of heat is going to be equal to the work done by the ideal gas. So we're thinking about ideal gas. Ideal gas. And during the isothermal process, equal to the work added to the gas. So it's the heat added to the gas, sorry. So work is equal to the heat. Heat is equal to the work added to the gas. Okay, so that will be for the isothermal process, where we have constant temperature or zero change in temperature. That's how we can tie them to the first law of thermodynamics. Now, another process that we'll talk about is actually all that I wrote here, the same representation. The next process we'll talk about, called adiabatic process, where we have no heat transferred during this process, or nothing can flow in or can flow out of our system. So the Q amount of heat is going to be equal to zero. This thing happens in extremely well insulated or in very quick process, during very quick processes. So the example of that will be, for example, very rapid gas expansion in the internal combustion engines. So that's where, when we're working with engines, the thermodynamic processes work there, applied. So it happens in extremely well insulated system or very quickly. Okay, so since we have no heat exchange in our system, then when writing the first law of thermodynamics again here, minus work. So this guy is 0. That means that change in internal energy is equal to negative work. So if the gas expands, it does positive work, and internal energy is decreasing and the temperature is decreasing. So because the temperature is not constant here, so you see that the relation between pressure and volume. So the temperature is not constant, also changing. That means that change in internal energy can be written in this form. It's not Kn or delta T, right? And so these two will relate to each other very nicely. Okay. So Q is 0. And the next two processes that we can look at are the isobaric process and isovolumeric process. They can show them together. And the first one is where the pressure is constant. So you can see change the volume of the gas, keeping constant pressure, or you can keep the volume constant and change the pressure. That will be isovolumeric. Also, sometimes it's called isochoric process, and that occurs at constant volume. And the work done in volume change, we can find how much work is done in this process. So it's useful to calculate that work. If the gas expands very quickly, then we know that the work we can also write down as force times the distance that it travels, right? So if we have a cylinder, so let's draw a cylinder. Again, we're looking at the expansion of, let's say, internal combustion, something, it's isolated system. So we have a piston here, supposedly, right? And we're gonna, something like that. We're gonna push that from this position down to this position. Okay. And so that will be the distance that it will pass. And this is the area of that piston. So basically, it will go down through the small volume, like volume down, when the gas expands during this process. And so we can write it also from here. I'm going to go here. From the definition of the force, we also know that the force is equal pressure times the area by which it's through which we're pushing it, and times the distance. But this one gives you the volume, so we get this equation up here that we have, that work done is equal pressure times change in, we'll say change in volume, because initially we had this volume, let's say, and then it's changing to different. So the small part is going to give you the change in volumes from one to another amount, the change in volume here. And that will happen. So this is true for the isobaric process, where the pressure is constant, but the volume is changing. But for isovolumeric process, when the volume is constant, that means the change in volume is 0, then we're going to have amount of work done that's going to be equal to 0. Okay, so this is for constant P, and this will be amount of work done at constant, should be constant volume. Okay, so constant volume, V equal constant. Okay. And so here's also a possible processes that combination of all these three together, where the pressure can vary. If pressure is not constant, then the work done is going to be calculated as the area under the pressure and volume curve. So let me see if I have, I just want to summarize this and then let's talk about this one and then I'll summarize this thing. So in isovolumetric process, which goes from D to A or A to D, work is going to be 0, and because the change in volume is going to be 0. Then in isobaric process, we will have, which is the one that keeps constant pressure but change in volume. We do have, let me write this down here. So for this guy, we have 0 work because change in volume is 0. For this one, we're going to have work done, which will be at constant pressure at point B, and the change in volume between B and A. Okay, and so the total work in the process ADB, so the whole thing is going to be these two together, and so basically was going to be this one. And if the pressure is not constant, then we cannot really use this equation. So this is for constant pressure. Just remember that, P constant. But if the P is not constant, then we can't really use that. And we'll need to come up with some average pressure, which will be calculating the area under the curve and finding the work that way. So to summarize the processes we just talked about, we have isothermal process where the temperature is constant and the change in temperature is 0. That makes the first law of thermodynamics to amount of heat is equal to amount of work because the internal energy is 0. In isobaric, when P is constant, I'll be writing this also in first law in implicit ways. We get that the Q is equal to internal energy plus work, and the work done in this case is pressure times the change in volume. In isovolumetric, so the constant volume process gives us change in volume is 0 and 0 work done. So the amount of heat is equal to the internal energy. And when we have adiabatic, so when there is no heat involved, then the amount of internal energy is equal to negative work done on the system. Right, so this is kind of a handy table to keep and have when doing some problems. You can apply this right away once you read the statement of the problem. So keep that handy, it will be useful. Okay, any questions on this so far? Okay, so let's look at one example of the first law, how it applies in isobaric and isovolumetric processes. Well, it's similar to the one I just showed here. So let's do a little more in detail. So an ideal gas is slowly compressed at a constant pressure of 2 atmospheres from 10 liters to 2 liters. And this process is shown in this picture. And it goes from B to D. So originally at 10 liters and slowly compressing to 2 liters. In this process, some heat flows out of the gas and the temperature drops. And heat is then added to the gas, holding the volume constant until the pressure and temperature are allowed to rise until the temperature reaches its original value. So we started at some point temperature at point B, and then at point A, the temperature is also going to be the same. And in this process, BDA, we want to calculate the total work done by gas and the total heat flow into the gas. Do I have this thing here? Oops. Okay. So by looking at the 2 processes that I just talked about, isobaric and isovolumeric, we can see how much work done in these 2 processes. So here, because it's the constant volume, then it means that no work is done, because we assume that the work is pressure times change in volume. So if heat goes out, that means temperature goes down. Then after we add heat and keep constant volume, pressure and temperature are going to be increasing until get to the same temperature at these 2 points, right? So BD is going to have work done because the change in volume is not 0. So here we can write, for this part, we can write the work is equal to pressure times volume final minus initial. Right. So in this process, there is no work done because change in volume is equal to 0. So here is 0. And so let's calculate the volume, the work in BD part. So let me, so we'll do BD path only. Calculation of the work will involve, and then we'll use first law of thermodynamics to do the rest of the calculation. So let me move this up. So I have space here to write. And what we have here, so pressure is given in atmospheres. We're gonna convert it into Newton per meters. So pressure is going to be equal 2 atmospheres times 101 times 10 to the 5th newtons per meter square. Change in volume, we're going to have a final minus initial, so it's going to be 2 minus 10 liters, so we're going to get negative 8 liters, and we're going to convert that into meters, so that will be minus 8 times, I'm going to use 10 to the negative 3rd meter cube. Okay. So, and it has to be negative because it's decreasing, right? And so the work done in this case, which will be pressure times change in temperature, will be 101 times 10 to the fifth. Oops, not 101, 2 times 202. So 202 times 10 to the fifth and times negative 8 times 10 to negative 3. So we get for the work negative 1.6 times 10 to the third joules. So they get right. Yeah, okay. 10 to the third joules of work. So, and this is going to be a total work that's done by gas in the process, or you can also say it will be positive work done on the gas. So this is done by gas, or you can say it's work is positive 1.6 10 to the third if it's done on the gas, Okay. So again, I still use my cheat sheet to figure out the right sign and whether it goes with the on or by. So I do encourage you to use those cheat sheets as well, to not to get confused. Okay, and for the next step, as the temperature is the same, that means in this isothermal process, that means that the change in internal energy is going to be 0, because it was proportional to change in temperature, if you remember. So this is going to be 0. And that means that from the first law of thermodynamics, it doesn't show here, but anyway, we'll have it here. This is also going to be equal to amount of heat minus work. Or that means, so since this is 0, then this is also 0, and that Q is equal amount of work. And we just calculated the work here. So that means heat is equal to amount of heat in this process negative 1.6 10 to the third, or 1,600 joules. And the negative sign means that the heat is flowing out of the system. So this much heat was flown out of the system or out of the gas in this process. Okay, so that's what the negative sign will signify in this case. Okay, any questions, guys? All right. Okay. Let's see. Oops. There you go. Let's look at a couple of more problems here. The work done in an engine, and then we'll look at the boiling water. How much internal energy is involved in boiling water out into steam. So did I include? Yeah, I have this couple of things here. Before I do this second problem, so I'll go over those previously learned concepts in heat. So work done in engine. Oops. Let me delete this for now, and then I'll add this later. In an engine of 0.25 mole of an ideal monoatomic gas in a cylinder expands rapidly and adiabatically against the piston. In this process, the temperature of the gas drops from 1150 K to 400 K. How much work does the gas do? Okay. So in any problem, as I said, it's a good idea to draw a diagram, picture of the process, and also write down all your word problem into variable problem. So let me move this up here and do that process. So let's keep it down here. The amount of gas, 0.25 moles, that means N is equal number of moles, 0.25. And it expands adiabatically. So if we know that goes adiabatically, which process is that? Which of one of the variables we can use here, take a use of. So if you go back to the so where's our adiabatic process? Anyone?
Q equals 0.
Okay, yes, Q equals 0, that's right. So since it's adiabatic process, we can also write down here that we have no heat exchange in this process. And in the process, the temperature drops from, so it will be initial 1150 K to the final 400 K. Okay. And we want to know how much work was done by the gas in this process. Right, so that's what we need. So if it expands adiabatically, okay, so if we can draw the gas, the piston in the form of a cylinder, again, we can do this to show it goes from one point to another, like that. So what we're going to take is the approach will be, we're going to look at the piston. So this is our piston, oops, right, to be our system. Sorry, is our surrounding, and the gas that's here is going to be expanding, is going to be our system. So the gas is system, and piston is our surrounding. So because pressure is not constant here, that means we cannot use the work that we can find through this equation, because in this one there is assumption that pressure is constant, so we cannot really use this one. So we're going to go with first law of thermodynamics. Let's take that, go from coming to that from the other side. Right. Because we do have a change in temperature, and that means that this term is not 0, is equal that, right? If you remember that. So we can use that one, but we do know this is an adiabatic process. That means this guy is 0. So we'll end up with 3/2 and RT delta T actually is going to be equal to our work, right? So let's do the calculation now. We can calculate the change in temperature, so the change in internal energy. So delta T is going to be equal final, or the delta U final temperature minus initial temperature. So we'll have here 3/2 and RT final minus T initial. And so that will be equal to 3/2 times 0.25 and times, I'm going to look up the gas constant. I do have it on the next slide also. It's 314 joules per mole Kelvin, mole times K. And the change in temperature will be 400 minus 1,500. Minus 150. Okay. So that will give us change in internal energy of negative 2,300 joules. We did that calculation. And so that also is equal to negative work. And so the work actually is going to be equal to 2,300 joules here. Okay, so this is what the amount of work done in the system by the gas during this process. Okay. Right. So let's take a quick break if you guys need before I go to the next problem, and I'll kind of outline some of previous concepts we used in heat, and so that we can do that problem here. Okay. So any questions, concerns so far? Okay. Okay, this part. Okay. Okay, so let's look at this example of the internal energy of boiling water as it becomes steam. And let's see how much internal energy is transferred in this process. So determine the change in internal energy of 1 liter of water, or mass 1 kilogram at 100 Celsius when it's fully boiled from liquid to gas, and it results in 1,671 liters of steam at 100 Celsius. So if you kind of think about the process, you have a boiling pot, 1 liter, and then you're going to catch everything as it boils away, becomes steam, into another container that will actually fill up with the 1,671 liters of steam. So assuming that this process is done at atmospheric pressure, so pressure is not changing, right? We want to see how much change in internal energy happened in this process. And as I was mentioning before, so here are some of the useful things from previous chapters. So heat is the energy transferred from one object to another because of the difference in temperature. But as you can see that here we have the temperature constant. What happens here is the change of phase. So from liquid to gas, phase change happens during the constant temperature. But in this case, also heat is exchanged. Okay, where did I put that thing here? Should enter that here in this slide, I guess. Okay, amount of heat. Let me add. And so the amount of heat that, let me add this in here as well. From previous chapter. Okay, this one. So I quickly do this, guys. So. Okay. Latent heat. I'll add this one too. Or okay. This one here. Okay. Let's quickly add this. Okay. Just have that also. So the heat, the latent heat we call, that's the heat required for a phase change, and it expressed in this following. So it doesn't have change in temperature. Okay. And some other useful facts about ideal gas, and we were talking about the standard temperature and pressure definitions. So defined as 0 Celsius or 273 kelvins. And when we deal with the gases, we usually tend to stick to kelvins. So if you're given a problem with this in the Celsius, make sure to convert them to kelvins. And the standard pressure will be the 1 atmospheres, or in terms of newtons per meter square is the 1.013. And for this standard temperature pressure conditions, volume of 1 mole of any ideal gas, whichever you can calculate, doesn't matter, will be 22.4 liters. Also, when we're talking about the gas, that doesn't change, the same type of a gas. Like if you have tire with air in there and you're changing the tire pressure and the volume, so you can assume that it is the same gas that's inside. So then number of moles is going to be fixed. Then you can use the relationship between first and the final states of that system and equate from the ideal gas equation that the number of moles is going to be the same. Then the ratio of pressure times volume over time is going to, over the temperature for initial state is going to be the same as at the final state. And so you can make use of these ones. And always also remember that temperature is in Kelvin and the pressure is the absolute pressure, meaning you have to have the pressure of the atmosphere, or usually denoted as 0, pressure plus the pressure at the gauge, or gauge pressure, also called. So that gives you the absolute pressure, P, or P absolute. So we'll just make it like that. And the heats are, due to the change of temperature, are the regular heat transfer, and the latent heats, it's either fusion or vaporization, will have constant temperature, but the changing of phase of that particular matter. And then also keep in mind to differences between the temperature and heat. So the temperature measures molecules' average kinetic energy, and the heat is a transfer of energy due to change in temperature. Okay, depending on number of molecules, you're going to have more internal energy if you have more molecules, and less internal energy if you have less molecules in your system. So this one, well, I already talked about. So let's do this problem of boiling water into steam and see how much energy is involved in this process. So I'm going to move this up. This guy. So here we have a phase change as a result of the heat, and we can use the latent heat of water to calculate amount of work. And as we do see that there is a change in the volume, because it goes from 1 liter to 1,671 liters. So the work here will be at constant pressure, because it does assume that the process is done at atmospheric pressure. So it's going to be the same constant, and change of volume like that. And the heat that's involved in here is going to be the latent heat. And for the latent heats of water or any other substances, you get the value of the latent heat from the table. So, or it's given usually in the problem. If not, then you can always look up in the table. So the amount of heat here is going to be equal the mass of the water, which gives you 1 kilogram, times the latent heat, which comes from the table for water, is going to be 22.6 times 10 to the 5th joules per kilogram. And so that's equal to 22.6 times 10 to the 5th. So the same thing. And so we can calculate the work done on that. It will be pressure times volume, change in volume. So let's do P times V final minus initial. All right, so this is our final volume. This is our initial volume. So what we'll have it for work is the pressure is 1 atmosphere, which is 1.01 times 10 to the 5th. Times change in volume, which will be, we're going to make the liters into meter cube. So that will be 10 times to the negative third meter cube, and that's minus 1 times 10 to the negative 3 meter cube. So here, so we get 1.69 times 10 to the 5th joules. So we got for the heat and for the work, and now using first law of thermodynamics will give us amount of heat in this process, minus the work. That will give us, so it will be 22.6 minus 1.69, or about 1.7, let's say it, times 10 to the 5th joules. So that gives us 20.9, or about 21. Okay, I'll just write 20.9 10 to the 5th joules of internal energy, or that was released during this process. Okay. Okay. What? So we do, we know that body does work, right? So we can apply the first law of thermodynamics to human body as well. So if the internal energy is not going to drop when we're doing some exercise, so then there must be some energy coming in, and if it isn't in the form of heat, then the body loses heat rather than absorbing it, like loses heat while you're doing the exercises, and it's also the one that transfers chemical potential energy that's stored in the food. So when you use this concept to find out how much energy that particular food will have, so then when you're consuming, you get that amount of energy from the food. So here are some interesting numbers. The metabolic rate at which internal energy is transformed in the body when you do different types of activities. So if you're sleeping, your metabolic rate is slower, of course. So if you give a comparison to watts, you can have an idea also. So it's about 60 kilocalories per hour of your metabolic rate, or about 70 watts. It's like a bulb, regular bulb. When you are doing light activity, like just walking around house and doing things moderately, so you spend about 200 kilocalories per hour. When you are running, you go up to 1,000. Biking, racing, 1,100 kilocalories per hour metabolic rates. Okay, so here is an example of energy transformation in the body. So how much energy is transformed in 24 hours by an average person who spends, let's say, 8 hours sleeping, 1 hour doing physical labor, moderate, 4 hours in light activities, and 11 hours working at the desk or relaxing. Okay, so the approach for this one will be the energy that transformed during each activity. So we have 4 activities here: sleeping, moderate work, some light activity, and then working, also kind of light activity, I would say. So we'll add all those activities and then multiply by the time that it takes to do that. So we get the metabolic rate in joules per second. So since there are 3,600 seconds in an hour, so the total energy transformed will be by 8 hours from the table here of sleeping, right? 1 hour of moderate physical work, so that will be this one, and then 4 hours of light activity, 230 here, and then 11 hours of, this is pretty a lot of work, okay. And so that all we add up together and then multiply by this time and seconds per hour, and then we get that amount of work energy transformed in this activity will be 1,000, well, no, can be 10 to the 7th, on the order of 10 to the 7th joule. Okay, so it's also an interesting thing, since we can look at the conversion between amount of work in joules and kilocalories. So it's approximately this much kilocalories. So food intake of this much would compensate for the energy output that you had during doing all these things. So remember, when you have a kcal showing here as capital C cal, that means kilocalories. So that's the same as this. So you have to add another 1,000 to that, okay, to consume, to compensate for the work that you've done during the day. So it's interesting. Okay. Oh. Where did my thing go? Okay, here, yeah. So that was all about first law of thermodynamics, and now we'll talk about second law of thermodynamics, which, so the first was another statement of the conservation of energy for a moment. So, and if we place a hot or cold, then the flow will go from hot to cold, but it will never happen in an opposite direction, right? There is no flow of the heat from cold to hot. So that cannot happen spontaneously. But if it did happen, then the conservation energy would still be conserved. But still, it doesn't spontaneously happen. So examples here, for example, if you are breaking the, dropping the rock or glass in this case, it hit the ground, potential energy is transformed to kinetic energy during the heat. And the kinetic energy is going into the internal energy. So what happens is the molecules in the vicinity of the impact at the ground, they start to move faster, and then temperature increases at that point. But the reverse part never happens, right? So this happens fine, but this never happens. So after they broke glass, nothing spontaneously will make it come back and get back to its original state. So we don't see the reverse. The rock from the rest doesn't suddenly jumps up back onto the mountain, and the internal energy doesn't go into the kinetic energy. So the energy could be conserved here, but we never see that happen. If it was happening, then the energy will still be conserved, but we can't really see. So, and there are many other processes that occur in nature, but the reverse of those doesn't occur. And so in order not to violate the first law of thermodynamics, the scientists back in 19th centuries, beginning or late 19th centuries, formulated a new principle that they call second law of thermodynamics. And it's all about the processes which occur in nature and which doesn't occur. So it obviously that the heat flows spontaneously from hot to cold, but it's not obvious for the reverse. And so they come up with so the definition of the second law of thermodynamics, the statement will be that heat can flow spontaneously from hot object to cold, but it will not flow spontaneously from cold object to hot object. And we're going to introduce a heat engine which is a device that changes thermal energy to a mechanical work, and it is important in developing the second law of thermodynamics. Okay, so what's the heat engine? So it's kind of easy to produce thermal energy by doing work. So if you're cold, you're rubbing your hands and you're doing work, right? You're heating up yourself, but the other way around, it's kind of hard. So to do thermal energy to make it work, it's much harder than the other way around. So the mechanical energy can be obtained from thermal energy only when the temperature goes from high to low. And some heat can be transferred in this process to work, and some can be lost. So to the heat engine, the purpose of the heat engine is to make mechanical energy obtained from the thermal energy only when heat can flow from high temperature to lower temperature. And to be useful engine, we can run that engine in cycles. Okay, so if you have several next to each other, you make a cycle, and to make that engine very more useful. So in each cycle, we will assume that change in temperature. I was going to do that later. Okay. Change in temperature is going to be 0. Then the change in internal energy is going to be 0. So the amount of heat at high temperatures, if you noticed here, I had labels here QH and TH, meaning the amount of heat at high temperature and the given temperature of high temperature. After the process happens, you get the amount of heat transferred to lower temperature. So amount of heat at lower temperature and the temperature lower, and then something so this is kind of an exhaust part of the thing, and this is going into the doing actual work. So the partial heat is transformed to useful work, and partial of it goes into exhaust to lower temperature. Okay, and so by, I'll show that a little bit later, the conservation of energy, we're going to assume that because that process is closed, so that from the high temperature we get work and exhaust, then the amount of heat at high temperature is going to be equal to the sum of the work done, useful, and then some heat that goes lost into the exhaust. So that's H and L are the operating temperatures of high and low temperatures. So we have here, right? So this is at the high temperature heat, and this is at the low temperature heat. So those are the steam engine and internal combustion engines. We'll talk about them in a sec. So we're going to derive the heat engine, and in order to drive the heat engine, we need the change in temperature. So if this temperature is the same during the intake and exhaust, that means that the exhaust work done on exhaust and the intake is going to be the same, and that means the net work is going to be 0. Oops, here. Clear this one. Okay. So I'm going to do. So the work done in the intake into the system and going to be equal to the work by the exhaust, and it's going to be equal to 0. And so that's going to, means that the net work is going to be 0 in that process. Okay. So this is an internal combustion engine, another type of the heat engine. The high temperature is obtained by burning gasoline and air mixture in a cylinder. So when this happens, then you generate the sparks here. And so these are spark plugs that work in an engine. And so as we keep going up and down, so to keep generating that and working the engine. Okay. So why does a heat engine needs the change in temperature difference? Well, otherwise the work done on the system in one part of the cycle will be equal to the work done on other cycle. And as I said, so the net work will be 0. And so in order to have the good efficient engines, we use the efficiency coefficient of the heat engine, which shows you the ratio between the work done on the heat during this process over the inputted heat. So this is the amount of heat when you start with at the high temperature, and then the amount of work that required. So the ratio of these two, if it's as close as to 1, will give you the most efficient engine. So from the definition of the heat from the conservation of energy that we defined earlier. So it was amount of heat at lower temperature plus amount of work. So if we plug this into the work here, so we'll say the work is equal to hot minus low temperature, heat at high minus low temperature, then we can see that efficiency coefficient is going to be equal to H minus L over the H, yeah, right, and that gives us 1 minus the Q low over QH. So if you have the coefficient will be the best if you have it equal to 0, if you don't have any lost or exhausted heat, and then the coefficient will be close to 1, but that's usually never happens. So it's always going to be less than 1, or it's going to be less than 100% efficient. So it's either 1. So if you get a number, you can convert it into percentage. What's the efficiency of that engine? And another thing that we can bring it up to, so how efficient the car is, we'll look at one example, and then we'll look at another efficiency coefficients. So if automobile engine has an efficiency of 20% and produces an average of this much, 23,000 mechanical work during the operation, how much heat input is required to get this type of output, and how much heat is discharged as waste from this engine per second? So we know that we have, let me move this over here. The efficiency is 20%, or it's in terms of the number, it will be 0.2%, 0.2, right? Converted from the percentage. And the produced mechanical work is 23,000 joules. Okay. So how much input is needed? So we want to know how much heat is needed at the high temperature so that we can get this much work at 20% efficiency, and what will be the amount of exhausted heat that will come out in that process. Okay, so if we kind of draw again, we have inputting some heat into system. So we're going to get it done some nice work, right? And then some is going to be exhausted into at a low temperature. Here, high temperature, oops, like that. So the amount of heat is equal to the work over the coefficient, efficiency coefficient, so from here. And so we can find that from the given values that we know, so it will be 23,000 over the 0.2. So that gives us about 115,000 joules of heat. So that much heat we need to input in order for to get this much work from our process. And so the engine needs this much per second, also we can say, or this much kilowatts of input into the system. And so now going back to finding the low temperature exhaust that will be generated in this case. So we can find it from this equation. So if we go here and solve for the low temperature exhaust heat, so we'll get QH times coefficient is equal to QH minus QL. This will be H here. And so the QL from here will be QH, oops, I forgot the L here, times 1 minus E. And so we did find the H already, so it's going to be 15K of joules times 1 minus 0.2 will give you 0.8. And so that's equal to 92 kilojoules of energy is exhausted into waste. Basically, it goes to the waste because the engine is only 20% efficient. Okay. So this is a pretty low efficiency if you look at it. So you need so much, you lose like 80% of your energy into nothing. So people have thought about how to increase the efficiency of the engines, and one of those people who worked on that was French scientist Sadi Carnot. And he examined the characteristics of an ideal engine. So what if we had an ideal engine that should be like the perfect and no losses at all? And so he came up with the cycle that he devised and called Carnot Cycle, where you have two adiabatic and two isothermal processes combined into reversible cycle altogether. So that adiabatic process where we have no heat exchange, and the isothermal, we have a constant temperature. And each process was considered to be reversible. So you can go back and forth. Meaning you do each process is so slow that it can be considered as a series of equal states, meaning no work is done in each process. And of course, in the real process, it's more faster and it's actually irreversible. But if you consider it to be an ideal system, then you can assume that that's the case. And so for ideal reversible engine, Carnot showed that, so here's this 4 cycles in together. Okay, just to look at the steps. So the reversible isothermal gas expansion process, and in that case, the system at high temperature, QH, heat from the heat source at the high expands and does work on the surrounding. So going back into the picture here. And then reversible adiabatic process, gas expansion process. In this system, the temperature is constant. Gas continues to expand and do work on the surrounding. And then the next one goes isothermal compression. So you go expansion, expansion, and compression, compression. And then the surrounding do work on the gas. And in the next adiabatic compression, the surrounding do work on the gas again, and the temperature. So here at the low temperature, then here temperature goes up. So just take times later and then look at this a little more closely, and has the steps and just describes how this works. And so he came up with the conclusion that if you have heats at operating high and low temperature, they should be also, the equation of efficiency should be also applicable to the temperatures at high and low operating temperatures. So meaning that you can also write for the ideal gas, not only the heats, but also the temperatures can be shown to have this relationship. So that the ideal coefficient of efficiency will be the difference between the low and high and low operating temperatures over the high temperature. And this is one that you can use to confirm the maximum efficiency of the engine that you can have. And here we can only see that we can get 100% efficiency only if the cold operating temperature is at 0, which is probably actually impossible to achieve. So the best real efficient engines they can achieve is 60 up to 80%, but no more. So that will be considered a real good efficient engine, a real engine. Okay, and so let's look at two examples that we have to see how we can check whether the engine is good or bad. Okay, and the efficiency of the steam engine. So if the engine operates at temperatures between 500 and 270, what will be the maximum possible efficiency of this engine? So here, meaning maximum will be looking at the Carnot equation, where the efficiency of ideal efficiency can it be. So that will be the maximum that we can achieve. So that will be 1 minus T low over TH. And so knowing these values for the operating temperatures, we can see that it will be, well, don't forget we need to convert this to Kelvin, right? So we get 270 plus 273 for both of them, right? So we get here 545 43 K over 773. And so that gives us, for the efficiency is about 0.3, and that means it's about 30% efficient. It's pretty low. So that's the maximum you can have. So in reality, if you're saying about 60 to 80% actual thing should be, so the actual engine will be about 20% in reality operating. So it's exactly similar to the previous example we did. So we do have a lot of losses anyway. And one other note, this is a pretty high temperature. And so usually engines are not working by themselves alone, but they're kind of put together in series next to each other, so that to make it a little more efficient, as I said, so then you can take the exhaust from one engine as an input to another engine and kind of use that lost heat as useful input to the next one. So when you put them in series like that, you minimize the amount of lost heat in that case, so make it a little more efficient. And so checking on this last example, we want to see whether the company that's trying to sell us an engine giving us right information. So they say that the engine heat input per second is 9 kilojoules at this temperature. That means that at high temperature input 435, the amount of heat can be inputted is 9 kilojoules. And the heat output per second is 4 kilojoules, meaning that the low is 4. And that happens at the low temperatures of 285. So to check whether the company is selling us good product or telling us truth or not, we can check the efficiency of the engine. And using the Carnot cycle, ideal. Because we know that for the ideal engine, the maximum efficiency that we can have will be the number that we obtain using the equation of T law over TH, right? So if the that is going to be equal to the amount of heats that they also say, then it's a good one. But if they're not consistent, so we'll see if it's low, whether it's lower or higher. We'll see whether they're telling the truth or not. So for the Carnot engine, if we use temperatures and do the calculations, we get what's already in kelvins. So 1 minus 285 over 435. 435. So that gives us the efficiency of about 0.34 or 34%, which is not that high. Okay, so if we do the calculation again for the efficiency based on the heat input and output, so we should get something below this number to be realistic, because this is the maximum that we can have. So if we get below this one, then we'll say, okay, the company is selling us and giving us right information. If we get above, then they are trying to scam us. So here we're going to go Q low over QH. And so what we're going to get here, 1 minus 9 over, 4 over 9. So what's the number here? Let me know. What do you get here? So 4 over 9. Get. One minus 9. So what I got, how much did you get, guys?
I got 0.56.
Yeah, I got 0.56. So that means this is about 56% efficient, which is not true, because based on ideal engine, it has to have, the maximum it can have is 34. So that means they are selling us a phony product. So it cannot have more than 35%, 34% efficiency. Okay. So that's the best way of checking out the maximum possible that you can have, and be sure that things are good. Okay. Right. So then let's look at one last thing in the engines. So 100% efficiency in an engine is basically, in reality, is impossible to obtain because that can happen only at the absolute zero, which is also unachievable in reality. And so the result of this is known as the third law of thermodynamics, meaning that no device is possible whose sole effect is to transform a given amount of heat into completely useful work. Okay. And so the heat engines were the ones that we looked at that transform thermal energy into work. And the refrigerators and air conditioning, they do that, just do the opposite of the heat engine. They transfer heat out of the cool environment to the warm environment. Okay, so, and the work is done by taking heat from the low temperature, like a fridge, and then he's trying to make ice, right? And then when you stand next to your fridge, you feel a lot of hot air coming out of from the bottom, because that's exhaust going into the hot place. So it's doing the opposite. When the engines did taking the hot and outputting into low, the refrigerators and ACs and heat pumps do the opposite. They take from the cold and output into the hot. So this work is done by electric motor. So you need some other type of work to help do that from low to high heat transfer of energy. So the perfect fridge where no work needed to take heat from low to high also is impossible. So it's something that also cannot be done. And so for the fridges and air conditioning, we talk about not the efficiency coefficients, but a coefficient of performance. So how well they will perform. And we define it as the ratio of the low heat to work. So work that's done to remove the heat from the system, right? So the more heat is removed from it, the better and more efficient or better performance the fridge will have. And so again, from the conservation of energy, we can also write that the heat at the high temperature is going to be equal to the work done and the heat transferred to lower temperature. So this is in and this is out. And you can calculate the coefficient of performance, again, using the heats that are involved, and also have the ideal or Carnot refrigerator or air conditioning, the maximum performance that it can have using the temperatures of the low and high and low operating temperatures. And so the heat pump also similarly. So we have coefficient of performance, which is the hot operating temperature heat over the work, and for heat engine was vice versa. Right? I just have it here for comparison. So the pumps are here and heat engine, that's what we did before. So this is what we're doing. We're taking input from the low. And so there is another thing that helps us to do that. And then we'll put it into the hot surrounding. Okay. So let's see how we can do make ice. If a freezer has a coefficient of performance of 2.8 and uses 200 watts of power, how long will it take to freeze an ice cube tray that contains 600 grams of water at 0 degrees? So we can see that we have here again going from water to ice, and this is the phase change, liquid to solid. So amount of heat that's going to be involved here is the latent heat again, because we're doing it at the constant temperature of 0 degrees. So the amount of heat is going to be, I'm going to be at low temperature, right? Mass times the latent heat of fusion of the water here. So water ice, we'll say that. So, and that will be the mass of the, what is the mass of 600 grams, or in kilograms, that will be 0.6 kilograms, and times the latent heat of fusion here, we can look up also in a table, and that's how much was it? 33, 10 to the 5th kilogram, joules per kilogram. Okay, so amount of heat here goes is about that we need to remove from is 2 times 10 to the 5th joules. Okay. So the freezer doesn't work. So this is amount of the power that it has. So the work will be amount of power over time. Right. So over time. So that's equal to 200 watts. And so the time is going to be 200. And also we know that the coefficient of performance, we have that is equal to lower Q over work. And so from here is equal to QL over the coefficient of performance. So when we plug in this into back here, so we can find that the time that we need to make that ice, 600 grams of ice, will be 2.8 where's my thing? Okay, 2 times 10 to the 5th over 2.8 and times 200. So units here are going to be, so not to confuse, so this is joules per second. This is joules per kilogram. Sorry, this should be joules, not joules per kilogram, joules per second. So we get the joules here. So the second there, joules cancel out. So we get about 360 seconds, which is about 6 minutes. So we'll require about 6 minutes to get all that ice converted to. Okay. So this example is on calculating the coefficient of efficiency of the heat pump. I'm sorry, that's, we're given a coefficient of performance. So we want to know how much heat we can also add in this process, and if it works as a heat pump, and then if we are turning it into air conditioning, how much the coefficient of performance has to be to have the same input and output. So that's the same way does probably you have in your homes, you have AC and heat that they operate as a heat during the winter and as AC during the summer. So that's exactly what this problem is describing here. And so we want to see how efficient those systems are. Okay, so let's see. So in the first case, we have it working as a heat pump. So we have coefficient of performance of 3, and the work is done at 1500 joules per second or watts. So we can say joules per second or watts are the same thing, right? This is per second, so it's going to be joules. So we want to know what is the amount of heat. So that's what we want to find when it's working as a heat pump. So for the heat pump here, we'll get that COP is equal heat over the work. And so the amount of heat here we can find to be 1500 times 3, basically. That's going to be 4500 joules. Okay. And now when it's working as a AC in this case, so we're going to take the low heat. So for the case of AC, we're going to take the low heat and from the inside the house and doing this much work again, 1500 per second. We're going to pump this much heat out to the outside. And so based on the conservation of energy, where we have QL equal to QH minus W. So if we rearrange that, the first one, okay, so we have QH is equal to QL plus W. So from here, this is equal that minus that. And so that's what we want to find out, how much of this we need to be able to pump out this much heat doing this much work. And so that's equal to 4500 minus 1500 joules. So we get 3000 joules of energy. Okay. For the low heat, low temperature heat. So the coefficient of performance for the refrigerator, air conditioner, will be the QL over the work. So that means it's going to be 3000 over 1500. Oops. So that gives us joules in joules 2 for the coefficient of performance when our heat pump is switched to be an air conditioner. So we only get coefficient of performance of 2, as opposed to when it's a heat pump, it has the coefficient of performance of 3. So it's better with the same input of amount of work that the engine does to provide all this to us, okay? Okay. Okay, and so let's do the last one about the entropy. We'll talk about, okay. And do one more example on that, and that will kind of summarize our chapter for today. So to generalize the second law of thermodynamics, the scientists came up in the mid-century with another idea of introducing entropy. And entropy is a function of a state of a system. So the system at a given state that has temperature, volume or pressure and mass, it can also have a particular value of entropy. So this is another state of the system that you can have and change. And like potential energy, the entropy by itself, just an S, we define it as S, doesn't work, but has more importance the change in entropy rather than the entropy of that point. So similar like a potential energy, the change in potential energy that has more importance than the potential energy at some given point. And so the entropy, change in entropy of the system is defined as the ratio of amount of heat that added to a reversible process at given temperature, which is a constant temperature. So here we have to have a constant temperature in the process to be able to calculate the change in entropy. And this is a statement of the second law of thermodynamics another way. So the total entropy of an isolated system never decreases. So you can know that everything tends to have always has high entropy. Okay, so the last example we'll look at is a change of entropy of melting ice. So if we have an ice cube of mass 56 gram and is then taken from a storage compartment at 0 degrees, and we're going to place it in a paper cup. After a few minutes, exactly half of the mass of the ice is melted, it becomes water, but still at 0 degrees. So we want to know what is the change in entropy of that ice water process. Okay. So because we also need the heat here, and again, there is a phase change in this process, that means we use the latent heat to find the amount of heat that is involved in this process. So again, the Q is equal to mass times the latent heat. And we've already done that. So the mass is 56 gram, but it says half of the mass of the ice is melted. That means we have 28 grams of the ice or melted the water. So here we need to use the amount of actually thing that's melted. So it will be 0.28 grams in kilograms. and times the latent heat, which was 3 times 10 to the 5th joules per kilogram. And so that gives us amount of heat that required to melt this much ice. That's this much ice is equal to 9.3 kilojoules. Okay. And so the temperature remains constant, 0 degrees or 273 K. So we can find the change in temperature in entropy as the ratio of the Q over 2T, so 9.3 kilojoules over 273. That gives you 34 joules per Kelvin entropy change. So here we kind of assume that no heat was or any entropy was accounted by the surroundings, so we calculated it as an isolated system. But if the temperature changes when then for a small change, we can use an approximation in the calculation. So for example, this next example gives us that possibility that if we have a sample of 50 kilogram of water at 20 degrees and we'll mix it with another 50 kilogram of water at 4 degrees, you see there is a change in temperature here. So we can use some approximation and the average temperature to calculate amount entropy involved in this process. So this will be the last example I'll do. And just to show how to apply that changing temperature here. I'm going to put this up here. All right. So we have sample at 20 Celsius, and also we have a sample at 24. So we can take, we can assume it's the same amount of water, and if we mix them, their final temperature are going to be 22 degrees, right? So initial temperature for one is 20, and we mix it together with another initial temperature of 24, then the final will have of the mixture of 22 degrees. Right. And because the masses are equal, so this is a more simpler problem. And we can use the specific heat and the calorimetry method to find the heats here, because we have change in temperature. So the Q here we can find from MC delta T. And the delta T for both cases is going to be 2, because the final minus initial 22 minus 24, or for this one also is going to be 2. So this is going to be 2 degrees. Right. So in one case, we're going to have from this higher temperature to 22, the heat flows into the cold water as it warms up. And for this one, the heat flows out of the cold, the other way around, into from here, out from here, and into from for the lower one, right? And so the total entropy change will be the sum of entropies of hot and cold waters. I'm going to say it hot and cold. And we can find the entropies for hot and cold by having an average temperature for hot and cold. Again, we're doing approximation So T average for hot. Which will be between these two, about 23 degrees, right? So it will be Q over 23. 23 plus 273. And for the entropy of the cold, we will have, again, the Q, and also over temperature of cold, kind of average, which will be between these two, so it's going to be 21. So it will be Q over 21 plus 273. Okay, so if we do this calculation, we're going to have, for the hot, we will have heat lost, so it's going to have negative value. And for the cold, we're going to get heat gained by the cold water, so we're going to have positive value for that. So if we do the calculation for the heats here, accordingly, then we get for the heat, I'm going to do generic calculation. So the mass is, I got it here, 50 times 4,001. Okay, let's do this, 50 kilograms times 4,186 for the specific heat of water, joules per kilogram per Celsius, and times delta T, which is 2 degrees, right? So from here, from this calculation, we get that the Q here for the hot is going to be negative because it's lost. So 4,186 joules over this temperature, 296, yeah. And here is going to be positive for 186 over 294. Okay, joules per Kelvin. So the total entropy will end up, so here we're going to get negative 14. Hot, negative 14 joules per Kelvin, and plus 1424, which is for the cold one. So the total change in entropy is about, so I'm going to say approximately, because we did approximations here, right? So it's going to be about 10 joules per Kelvin. Okay. All right, so any questions, guys? Good to go. So I did post here an interesting webinar. Try to watch it. Let me go back here and show that. So I'm going to finish it on here already. So it is, wait, is it online? It's not on the one on your copy, or is it on your copy? Okay, so copy, paste. Okay, so try to copy and paste this into your browser and see. It might take several minutes to load. Let's see. Okay, let me enter this here. So see if you can copy and paste in the browser and open that webinar. It's an interesting webinar about thermodynamics and how the heat engines that we use here are applied to one atom, single atom, to create a single atom heat engine. So it's a long one, but you can watch only half of it if you, to kind of, because it gets a little more complicated afterwards, but to kind of see the cycles that are happening in that single atom heat engine is exactly the same things that are happening in real engines. And two questions for you. Will you recognize the Carnot cycle there? And if yes, if not, what's the name of the cycle that's there in that single atom heat engine involved? I'll post that question on Canvas for you to enter your answers there. Let me know if you can open the web, if it opens. It might take a while to load, because when I tried it from different places and it does work, but sometimes takes a little long. Okay, perfect, great. So watch sometimes.
Where's the link? Where's the link for the webinar?
I just posted in the chat.
Okay, thank you.
And I'll post this, I'll update the file that I uploaded with this one, so you have that on Canvas as well. Let me do that right away before I forget. Okay, so where am I now? Here. Okay. So, Joules, it will be okay. That's not the one. Is that the right one? Let's do page. Okay. Why is it showing up? Okay, so it shows up here. Document. All right, so check and see. Okay, you should have the new link to the PowerPoint slides, and I also included the link to webinar in this one as well. So see if you should be able to see that. And I'll create some place for you to put the answers there. Okay. All right, great, thank you. So everything is there. And we have, guys, any questions, anything? We're done with this chapter today, so.
I don't have any questions on the chapter, just on the work we're supposed to do for the next week. I see that the homework is already posted and due by Tuesday. But the lab, what exactly are we supposed to turn in for the lab? Are we supposed to turn in a full lab report? Or
no, you don't need the full lab report. Just do the work, calculate the specific heat of each of the three samples that you had and fill in the table and answer the questions. So you don't need the full lab report.
All right, thank you for clarifying that. And then the textbook is still not working. I still have not been able to access my MATLAB or the physics lab at all.
The mastering?
Yeah.
Or does anyone has access to my mastering?
I do.
Okay. Can you, Kyla, maybe share the info how you got it working?
Mine was working from a pre-existing account, so I don't know how to set it up or buy the access code. Mine automatically just popped up and enrolled me in the course.
Okay. So you had the previous account. That way. So how about you, Selena? Do you have a previous account, or so you'll have to create it when you click on? Let's see. Sean, do you have already your account, right? So can you access My Pearson? Yeah, because you already had it in the previous one.
Yeah, I have it from last semester. So we're doing the homework like not through there anymore. We're just doing the worksheet that you posted.
No. We're doing on that still on my mastering. I just put the worksheet in case if you want to start working, but you don't have the access, as Selena can't access it yet until she establishes the access. But it should.
I think now it's starting to work again. Before, when I clicked it this morning and last night, it did not load, but now everything's loading. So I'll probably be able to do it.
Okay, yeah. If you started up account already, then maybe it took a time to get activated, or I don't know.
That's possible.
Load the thing. So I'm gonna open the homeworks there. So please, do the homeworks on that. And if you need some guidance how to work through in my mastering, the first one, introduction to my mastering, will be helpful for you to go over. Other than that,
are the homeworks actually posted on there? Because I'm looking at it right now and I don't.
Not yet. I'm gonna open them right now. So I need to go into my mastering. The dates did not convert to my current dates, so I need to change the dates. Let me do that. Silence. Okay, so edit. Okay, let's do this. Okay, I just opened the first two, and I'll change the dates for the other ones later today. Okay, so just make let me know if you see the first two, the introduction and chapter 15. Okay, let's see.
Yeah, I see them.
Professor, for
Yeah.
the questions for the webinar, did you want us to turn them in or keep them? Because online there's not a submission button for it.
Oh, I'll open the submission button on.
Okay, thank you.
Yeah. So Rustin, you were saying about, oh, he left, or is he still here? Oh, he's still here. If you already had an account, then you will not need the access code. But if you're just registering and you didn't have it before, then you will need to have an access code. So you have to buy it. Is it $80 now?
Yep.
That's what you're asking for?
Yep.
Oh, it went from, I think it was 60 before, now it got $80. Okay. So you didn't have the account before? You haven't used my mastering?
I had an account with Pearson before. I think I used it for math. I don't remember which one, but that was like 2 years ago, maybe 3 years ago.
Oh yeah, no, that's
I didn't use this for physics 201.
Oh,
That's fine.
Okay. So you can sign up for 15 days for free for now, and let me know if you need any help with that. No, the access codes, I think you should do it directly on Pearson. Yeah. Bookstore, for some reason, they usually sell it, the whole thing, for some reason. I don't know why it was like that. So I try to get only my mastering thing, but yeah. So
Is anyone else here on the My Mastery thing at the moment? Students?
students. Oh,
I'm talking to them at the moment. I want to see if any of them are on it. Just want to compare what theirs looks like to mine. Mine at the moment is just stuck on the loading window, where it's just like spinning in circles, waiting to load. Just, I don't know if it's the servers are bad or if it's just being slow to um, unlock the content. I don't know.
That was happening to me a while ago, like before the class started. So
Okay.
it wasn't like responding very well either. So now I see it and it's fine, but before that was my issue.
Okay, I have 3 people showing up that are on. Just came up.
Bear with.
Thank you. I'll be back in a second.
Did I miss? What did I miss? If anything.
Nothing. I think we're done. I don't know though. I don't know where she went.
She just said she'll be right back this one, but pretty sure you're right. We're done.
I was gonna say, I know you guys already have set up a group me, but I like the functionality of Discord better. So whenever I post something, it's just gonna go straight into Discord.
So you're able to get on? Did it load or is still on the loading process?
For me, it's still in the loading process.
Are we done for the day, Professor?
Yeah. So does your mastering work fine?
Yeah, I'm in. Yeah, I see the assignments and everything.
Okay. All
Yeah,
right.
mine works as well now, so I'm good.
Okay, so Ralston, maybe because you just set it up, it takes some time to.
Yeah, that's what I thought.
Time. It's fine.
Yeah, so send me an email if you don't get an access, and meanwhile you can start working on those problems that I posted on Canvas, just to get familiar what things you're going to be working on. But once it gets going, then complete it on my mastering.
All right, then thank you so much, then, Professor.
See you on Tuesday.
Okay, see you on Tuesday.
See you on Tuesday,
Thank you.
Professor. Aaron, bye-bye.
Bye.